Hello friends, my name is Mayank Choi and welcome to my YouTube channel. Today we are going to learn advanced RAG search, and this one is all about hybrid search. If you have been building RAG pipelines and wondering why your retrieval sometimes misses obvious mismatches or returns semantically distant result, you are going to love what we cover today. We will learn keyword search, vector search, and how to combine them using an ensemble retriever with LangChain. By the end of this video, you will have a working hybrid RAG pipeline running on a real research paper. Let's get into it. Don't forget to hit like and subscribe. It really helps the channel grow. Let's start the fundamental before we write any code. Hybrid search is the combination of two distinct retrieval approaches, keyword search, vector search, fused together using an ensemble retriever. On the left, we have keyword search. This is actually not a new idea. Google pioneered this decade ago using TF-IDF and paper PageRank. The idea is simple. Find documents that share the exact same words as your query. The math produce a sparse vector. Imagine a massive list of all words in your vocabulary, and only the words in your sentence have no non-zero values. On the right hand side, we have vector search. This uses modern transformer based embedding models. Think sentence BERT, BGE, or OpenAI embedding to convert your sentence into a dense vector where every dimension carries meanings. The two sentences like the dog ran fast and the horn sprinted. Will have a similar dense vector even though they share zero words. Neither approach is predicted alone. Keyword search misses synonyms. Vector search can miss precise terms. Hybrid search gives you the best of both worlds. I would like to make a small announcement before we proceed further. The 2026 AI engineer is not what most people think. If you have been an IT for 10, 15 or even 20 years, you are probably seen all the hypes around AI, and maybe you have thought, do I need PhD? Do I need to learn advanced mathematics? Do I need to become a machine learning researcher? The answer is no. The biggest misconception today is that AI engineer means building neural network from scratch, training massive model, and spending years studying deep learning theory. That may have been true for a few years ago, but in 2026 the role has been changed dramatically. Today's AI engineer and orchestrator, a forward deployment engineer. Instead of building model from scratch, you are connecting AI model with business problems. You are building RAG applications. You are creating AI agents. You are integrating AI into existing system. You are deploying AI solution that people can actually use. And here is the exciting part. Most experienced IT professionals already have many of these skills needed. If you are a system administrator, DBA, network engineer, cloud engineer, IT manager, architect, or software engineer, you already understand system integration, troubleshooting, automation, security, and deployment. Those skills are incredibly valuable in AI world. The challenge isn't that you need to start over. The challenge is learning the AI layer. You need to understand prompt engineering, AI APIs, vector databases, embedding, retrieval augmented generation, or RAG, you can say, AI agents, deployment and monitoring. Once you learn these building blocks, you can start creating powerful AI application. That's exactly why I created AI Pioneers. AI Pioneers is an 8-week live cohort designed specifically for experienced IT professionals who want to transition into AI, getting lost in years academic theory. Over the course of 8 weeks, we will go through from Python fundamental all the way to building and deploying real world application. Week 1, you will learn for AI and understanding the AI landscape. Week 2, prompt engineering and working with large language model. Week 3, API and LangChain. Week 4, embedding and vector databases. Week 5, building your first complete RAG application. Week 6, advanced RAG technique and evaluation. Week 7, AI agents and deployment. Week 8, it's a and we have to do the capstone project and demo day. By the end of the program, you will have your own AI portfolio project, a deployed AI application and hands-on experience building solution and organizations are actively looking for. This is not about becoming an AI researcher. This is about becoming an AI builder. Someone who can take business problems and solve them using modern AI technologies. If that sounds you interesting to you, cohort 2 is now open. You will get live session, hands-on projects, recording, community access, mentorship, and a capstone project that you can showcase on LinkedIn and in interviews. If you like to know more information about this, reach out to me directly over the LinkedIn or through Telegram. Before we go further, let us have a quick revision for the TF-IDF, term frequency, inversion document frequency. This is the backbone of keyword search, and if you understand this, you will understand why BM25 works, why sparse vector looks the way they do, and why hybrid search give better results than pure vector search. What is corpus, document, and vocabulary? Before we even touch the formula, we need three definitions. First, the corpus. Whenever we fetch data from the internet, load a PDF, or collect any text, that entire collection is called the corpus. Second, the document. Each individual sentence or paragraph inside the corpus is called document. So, corpus contains documents. Third, the vocabulary. From all those documents, we extract every unique word. That full set of unique word is called the vocabulary. This matters because dimensions of your TF-IDF sparse vector equal the size of your vocabulary. If your vocabulary has 10,000 unique words, each document become a 10,000 dimensional vector, and most of those values will be zeros because most words don't appear in any single sentence. This is exactly what makes sparse. Now look at the first formula, term frequency. TF, T text, number of items, terms, T appears in the text divided by total number of terms in the text. So term frequency simply asks how often does the word appear in this specific document. Example, if the word keyword appears 3 times in the sentence that has 10 words total, the TF scores or keyword in that sentence is 3 divided by 10, which is 0.3. Simple, the more word appear in document, the higher its TF score. Now second formula, inversion document frequency, IDF. Now the second formula is basically IDF T corpus log total number of text in the corpus divided by number of text containing term T. IDF asks how rare is the word across all document in the corpus. Think about the word the, the in it appears in almost every sentence. So the denominator number of documents containing the is very high. When you divide total number of documents by a large number, you get something close to 1. Log of 1 is 0. So the word gets a near 0 IDF score. Now think about the word BM25. It appears in a very few document. So denominator is small. So the divide by small word, you get a large number. Log of large value is high. So BM25 gets a high IDF score. IDF rewards rare, distinct word. It punishes common stop words. The final formula is simple. Multiplication. TF, IDF, T, text, comma corpus equals to TF T comma text multiply by IDF T comma corpus. So a word gets a high TF-IDF score only when two numbers are true at the same time. It appears frequently in this specific document. High TF, it is the rare across corpus high IDF. If if either condition fails, the score drops. Here is a simple small implementation of TF-IDF and for all three formulas. So in this, the word keyword appears often rare in corpus. So TF is high, IDF is high, TF IDF score is very high. D appears often, common everywhere. So TF is high, IDF is low, and TF IDF will be low. If we have, so in this corpus we don't have that word, but if we have, so BM25, if I'll take in the third scenario, appears once, rare in corpus. So TF is low, but IDF is high. TF-IDF score is basically medium. Filter word rare everywhere. Low TD, low TF, low IDF, TF-IDF score very low. Slide. Before diving into the code, let's understand where we are in the broader RAG retrieval landscape. In previous RAG videos of my channel, I focus almost entirely on the data ingestion phases, chunking, embedding, storing in vector database. The retrieval side was always basic, a simple similarities search. But real retrieval has many techniques and we are going to go through all of them one by one. Today we are covering hybrid search. The remaining techniques sentence window, self-query, parent document and hide will each get their own dedicated video. The reason naive retrieval fall short is simple. If your query uses different words than the document, similarity search alone will miss it. And if your query uses very specific technique terms, semantic search might dilute them with loosely related concept. Hybrid search is the immediate upgrade. Hybrid RAG architecture. Let me walk you through the full architecture so you understand every component before we look into the code. We divide it into three phases. Phase 1 is indexing. We load the PDF file, split it into 200 word character chunks with 30 character overlap. Convert those chunks into the dense embedding. The BG base EN high model running locally via Hugging Face embedding and store them in ChromaDB. Phase 2 is retrieval and this is where hybrid search lives. When the user sends a query, we run it through two retrievers simultaneously. The dense retriever does vector similarity search using embedding. The BM25 retrieves does keyword based sparse retrieval, ensemble retrieval, then blend the two scores 30% vector and 70% keyword and returns the top K document. Phase 3 is generation. The context document are passed Zephyr 7 billion loaded at 4-bit NF4 precision via bits and bytes which generates the final answer. We will use LangChain package for EnsembleRetriever and Retrieval QA for our notebook. Before we write a single line of code, I want to make sure you have a rock solid mental model of RAG architecture because once you see the diagram clearly, every line of code we write will just make sense. So let me walk you through this architecture step by step. I'm going to break it into three phases. You will hear me say these names throughout the series: ingestion, retrieval and generation. Every RAG system, whether it is use naive search, hybrid search or re-ranking, follow these exact phases. Let's go. Ingestion. Look at the left side of the diagram. You can see a node label as data. This is your raw source. It could be PDF, Word document, website, a database, anything in your demo today. It is a PDF file, research paper could be, we will have. Now from the data node, you see 3 arrows going into separate chunking box. Where? Why 3? Because in practice your data is too large to process in one piece. We split it into smaller manageable pieces called chunks. Each chunking box represents one chunk, one piece of your. In our notebook, we will use recursive characters text splitter with chunk with size 200 and overlap 30. Overlap character means the last 30 characters of chunks 1 become the first 30 character of chunk 2. So we don't lose the context at the boundary. Now from each chunking box, you see a red arrow going into the green embedding box. This is where we convert each chunk into a vector, a list of numbers that capture the meaning of that chunk. In our pipeline, we use BGE based embedding model via Hugging Face, which will be running locally on Colab GPU, no API token required. And finally, all 3 embedding boxes have a green arrow following down into the database node is your vector database. The blue diamond shape is your vector database. In our demo, we will use ChromaDB running in memory. So summarize, phase 1 ingestion, data, chunking, embedding, store into the database. The whole left side green flow is called ingestion pipeline. You run this once embedding sits in the database waiting to be queried. Now come to retrieval part. Now look at the right side of the diagram. You will see a brown circle labeled user. That is the end user person asking a question. The user sends a query. You can see the label on arrow query. That query flows down to the orange embedding box. Notice this is the same embedding model we used in the phase 1 BGE base. We convert the query into vector using same model, so the query vector lives in the same space as document vector. Now that you see label similarity search, this is where we compare the query vector against all documents vector in our databases. We calculate cosine similarity, the angle between vector and the documents with the smallest angle, the highest similarity win. Now here is the important part, and this is what makes hybrid search different from naive RAG. In the naive RAG, you only have orange flow. Dense vector similarity search, you get back 3 documents. That's it. In hybrid search, we run 2 searches simultaneously. Dense retrieval, keyword retrieval. What is dense retrieval? Using the BGE embedding stored in the ChromaDB, this finds documents that are semantically similar to your query. Even if the words are different, it finds conceptually related chunks. Keyword searching using BM25, which we wire in a separate retriever. This finds document that contains the exact word from your query, precise literal matching. Both retrieves return their top 3 documents. So we now have up to 6 candidate document EnsembleRetriever from LangChain Classic. Then blends the 2 sets reciprocal, rank refusion, a weighted combination where we assign 30% of weight to the dense retriever and 70% to the keyword retriever. Why 70% retrieve? 70% to keywords? Because we are working with the technical research paper where exact terminology matters. Words like rack, token, model, or abstractive question answering need to be matched precisely. The output of the ensemble retriever is the orange box you see in the diagram, labeled rank result. This is the top K blended list of the document that the system believes the most relevant of your query. To summarize phase 2, this part, retrieval part, query, embed, similarity search, dense plus keyword, ensemble, rank results. Now third part, which is I call phase 3, generation part, the pink flow. Now the rank results box has a pink arrow going into the LLM diamond to the right. The pink diamond is your large language model. In our demo, we'll use Zephyr 7 billion loaded from the Hugging Face 4-bit NF4 precise via bits and bytes. We use Retrieval QA chain from LangChain Classic. The chain takes your rank document and stuff them into the prompt as context using the stuff chain type. The LLM reads the context and generates answer grouped in what was retrieved. And finally, you see the pink arrow going back up from LLM to the user circle. That is the answer being returned. The loop is complete. To summarize phase 3 generation, rank results, LLM, Zephyr, answer and users. The critical distinctions, what makes this hybrid. Let me call this output one more time because this is the whole point of this video. In the naive search, naive rack, phase 2 basically retrieval uses one retrieval, dense vector similarity, you get 3 documents. If your query uses exact technical terms, semantic search may dilute them in hybrid track. Phase 2 uses 2 retriever running in parallel, dense and keyword BM25. You get up to 6 document, richer, more precise context. The ensemble technique blend both with alpha weighting. The LLM gets better context generation, generates a more accurate answer. This is entire architecture, 3 phases, 2 retrieval path in phase 2, 1 blended rank results passes to LLM. I hope you understand. Now that you have this architecture logged in every code in cells of our notebook will map directly to one of these boxes and arrows, which I say dense retriever. You know which node is that. When I say ensemble, you know exactly where that sits in the flow. If this walkthrough helped, please hit the like button, subscribe to the channel and share this with anyone learning RAG. It genuinely helped me keep making this content. Thank you. So go back to our slide. So now we are at Google Colab. Let's start building our RAG. So if you are building RAG pipeline and your retrieval is missing results, sometimes giving you vague answers, sometimes completely missing the point, this video is going to fix that. So by the end of this video, you will have a working hybrid RAG pipeline running on a real research paper, and you will understand exactly why it performs better than Naive's approach. Make sure your Google runtime is set to T4 GPU. Runtime change, you can go to runtime and change runtime. One second, you will go to change runtime and then T4 GPU. Do that now before you start. Okay, we have the notebook is open. So first of all, the GitHub link for this notebook is in the description. You can follow along or run it after the video. First of all, we will install all the dependencies. Let me copy paste. So here I am installing all packages we need. A few important ones to call out: PyPDF for reading PDF, LangChain community, this is where most of the retrieves and loaders live now, rank BM25. This is the BM25 keyword search library that LangChain wraps internally. Bits and bytes and accelerate. These are required for loading the quantized model on GPU. And LangChain Classic, this is where EnsembleRetriever and Retrieval QA live now. Let's run this. Let me add one markdown on top of this. I'll have to put that in later. What is markdown? Let me put this. What is hybrid search? Hybrid search, I'm just revising and repeating again. Hybrid search is a combination of two things: keyword search and vector search. Keyword search uses TF-IDF and or BM25 and produce what we call a sparse vector. Most values are zeros. Only the word that actually appears in the document get a non-zero score. Vector search uses transformer based embedding model and produce a dense vector. Every single dimension has a value. This captures semantic meaning. The core formula you have seen earlier for hybrid score. Plus, I want to talk about why naive retrieval isn't enough. Let me also add this one because I have to add that as well. Later I will add the complete description. Why are we doing this at all? What is wrong with the naive approach? The naive approach is just dense vector similarity. You embed your query, find the closest document vector, done. And the most tutorial that is where it stops. The problem is if your query has very specific technical terms, semantic search dilutes them. It finds conceptually related documents but misses the ones that contain the exact word. And if you only do keyword search, you misses synonyms and paraphrases. You can see in this roadmap that hybrid search is actually just second technique. We are going to cover all of them in these coming videos. Sentence windows, self queries, parent, document hide, all of them, but hybrid is the first most practical upgrade. We have also discussed the architecture diagram. Now let's me put the imports. So here I am importing TF-IDF vectorizer from sklearn. This does all the TF-IDF math for us. Cosine similarity to compare vectors, numpy for array operations, and re is for regular expression. We need that for the pre-processing steps. We have a document. Let me add this one. So I have 5 sample document here, and notice the word keyword appears across multiple documents in the different position. My query is keywords based search. Now watch what happens when we rank these documents using TF-IDF. The document where keyword appears more frequently will score higher. That is TF in action. So here I am cleaning the text. Two things happening. Let me make it a big. I am not sure whether you can read it. Anyway, two things happening. First, lowercase everything. This is important because without these steps, keyword with capital K and keyword with small k are treated as two different words. That would break our vocabulary. Second, remove punctuation using regular expression. Hyphen, full stop, commas, all gone. Look at the output. This is your clear corpus. Okay, so now watch this carefully. Fit transformer does two things at once. First, it builds the vocabulary, all unique word across all 5 documents. Then it converts every document into TF-IDF vector so that vocabulary size. Look at the matrix output. Rows are document, columns are vocabulary words. Look at how many zeros there are. Most values are zeros. This is what sparse means. Only the words that actually appears in the document get a non-zero values. The vector size is your vocabulary size, not 768, not 1536 like dense embedding. Just the number unique word is in your corpus and most positions are 0. This is the fundamental difference between a sparse and a dense vector. Important. Notice I am using transformer here, not the fit transform. Why? Because the query must be encoded using the same vocabulary we built from the document. If I call fit transform on the query, it would build a brand new vocabulary from just that one sentence and the comparison would be meaningless. So transform only same vocabulary, new vector, the cosine similarity. This measures the angle between the query vector and the document vector. Smaller angle between higher similarity. Look at the scores. Some documents scores higher. Those are the ones that shares more TF-IDF weighted word with the query. Now come to ranking. So arcsort give us the indices, sort by similarity. The colon -1 reverse it so highest score comes first and the flatten converts it from 2D array to 1D. Look at the result. The document where keyword appears multiple times rank at the top. This is exactly TF doing its job. Term frequency, more occurrence in the document. Higher TF, higher final TF IDF scores higher rank. Document where keyword does not appear score 0 and go to the bottom. This is keyword search raw from scratch. In our real pipeline, BM25 does the same thing but the better length normalization on top. Now let me show you the other side, vector search and dense embedding. In practice, this uses BGE base embedding model which produce 768 dimensional vector. To keep this demo simple, I am using toy 5 dimensional vector, but the exact same logic applies. Dense embedding, let me copy, execute. Look at the embedding values. Let me go down. Okay. Look at the embedding values. Every single number has a value, no zero. That is what dense means. Each dimension has here represent a learned feature from the neural network. Things like sentiment, topic, entity type and individual words. So when you do cosine similarity on dense vector, you are comparing meanings, not exact word. Two sentence about dogs and hound would score high similarity even though they share no words. That is the power of dense. But it is also means if your search for BM25 retriever, the dense model might match document about information retrieval in general, not a specific term. That is why we need both. Let me give you an analogy that makes this stick. Imagine this sticks. Imagine two librarians. Librarian has a card index of every exact word in every book. You ask for bunny, she checks the index, it's not there, she come back empty, perfect for exact term, useless for synonyms. Librarian B has personally read every book and understand concept. You ask for bunny, she thinks small animal, brings you rabbit book, great for meaning, but might miss precise technical jargon. Hybrid search put both librarians to work at same time. Each score every document independently. Then we blend their score using alpha weight. The ensemble retriever is the manager who takes both list and produces one final rank result. Okay, so now we move from conceptual demo to the real pipeline. Make sure you have uploaded the PDF file to Colab. The file name is the full name I have written in the code exactly. You can download it from the Neura IPS website, or I will link it into the description. Go to documents, storage, go to storage. I have a book here. Let me download the book or upload the book basically. Let me, okay, says okay. Book has been downloaded. Let me execute the cell. In fact, if you want, you can again copy path from here and paste it here. Control C, Control V. Now just execute this. So PyPDF reads the PDF page by page. Each page becomes a LangChain document object with page content and metadata. Note, I am importing from LangChain text splitter. Earlier version was langchain.textsplitter. So please, if you are using old libraries in your any other notebook, please correct it, because in the old means they have changed their libraries to langchain.textsplitter to langchain textsplitter now. Now we have to do chunking. This is done. Book has been uploaded. Two parameters here. Chunk size 200 and chunk overlap 30. Chunk size 200 means each chunk is approximately 200 character. This is intentionally small for a research paper, so we get precise retrieval. Overlap 30 means the last 30 character of chunk number 1 becomes the first 30 character of chunks number 2. Why do we need this? Because if sentence spans two chunks without overlap, you lose that context at the boundary. Overlap prevents that. Look at how many chunks we get. A typically research paper like this will give you a few hundred chunks. Each one is a candidate context document of retrieval. Embedding model. So here I have to give a access for my Hugging Face token. Let me grant access and then I'll show you the Hugging Face token. To see that token, you have a secrets here. Once I grant this, it becomes enable. Either you can enable it before or after while it is asking. So Hugging Face token, it is asking and I gave that access. So it is required to from Hugging Face. If you don't know about anything about Hugging Face or you want the details, let me know. I'll have to prepare. Either you can go through my previous videos or I will go through again, or I'll prepare again another video for Hugging Face. Important difference from older tutorial you may have seen. I'm using Hugging Face embedding here, not Hugging Face inference API embedding. Let me go up a little bit. This means the embedding model downloads and run locally on your Colab CPU. GPU. No API token, no internet call during embedding. Once downloaded, it works offline. The model BGE base EN version 1.5 768 dimensional dense embedding, open source, top performer on the MTEB key leaderboard for its size class, ChromaDB and EnsembleRetriever. So from documents, take our chunks, embed each one using BGE and stores the resulting vectors in ChromaDB. Quick note, ChromaDB is running in memory mode. That means when you stop the Colab runtime, the data is gone. If you want persistent, you pass persistent directory ChromaDB. I have that commented in the notebook notes. Then as retriever wraps the vector store as LangChain retriever. K equals to 3 means return top 3 results by cosine similarity. This is your dense retriever, part 1 of the hybrid pair. Now let's build the keywords side. BM25 is a production grade version of TF-IDF. 2 improvement over raw TF-IDF. First, document length normalization. Without this, a longer document would always score higher just because it has more words. BM25 divides by normalized document length, so long and short document compete fairly. Second, the term frequency saturation in raw TF-IDF. If a word 50 times, it stores 50 times higher than a word appearing once. BM25 caps this using a saturation function. After a certain frequency, the scores stops growing. BM25 is the default search algorithm in Elasticsearch, the same algorithm that power enterprise search for years. We are plugging that directly into our RAG retrieval. Notice BM25 Retriever is from LangChain community, Ensemble Retriever is from LangChain Classic. There are two different packages. That is why we installed LangChain Classic separately. From document takes our same chunks that and build a sparse keyword index from them. No embedding model, no GPU needed for this part. It is pure text matching. K equal to 3 means same as dense retriever. Return top 3. Now we have two retrievers. Time to combine them. Alpha weighting tuning these ensemble. Here is the formula. Hybrid score alpha times dense plus minus alpha times square. Alpha equals to 1 pure vector search only. Alpha equal to 0 pure keywords only. Alpha equal to 0.5 equal weight to both. We are using 0.3 for dense and 0.7 for keyword. So 30/70 split favoring keyword. The reason is this research paper has very specific technical terminology. Word like RAG token model should match exactly, not semantically. If you are building a RAG chatbot over journal text, flip this. Give more weight to dense. If you are building over legal document, financial, filling, medical records, give more keyword heavy. This is your tuning knob. Ensemble retrieval. Let me copy paste. So the ensemble retriever takes a list of retrieves and a list of weight. Simple internally it uses reciprocal rank fusion RRF. Now raw score blending RRF looks at the rank position. So each document from each retriever and combines those ranks with the weight. So if a document is ranked first by BM25 and second by dense, it gets a high combined score. If a document only show up in one retriever, it still get included but the lower combined weights. That is how we go from 3 documents to up to 6. Now we load the LLM. This is the generation part, phase 3 for architecture. We are using Zephyr 7 billion loaded with 4-bit precision. Without quantize, Zephyr 7 billion need about 14 GB of GPU memory in FP16. That does not fit on a free Colab T4 which has 15 GB. With 4-bit NF quantize via bits and bytes, we bring that down to about 4 GB. Fit comfortably. Quality loss is less than 2%, so we get the 7 billion parameters model running for free. Make sure your GPU runtime is active before running the next cell. Setting up the import and model name Zephyr 7 billion beta from Hugging Face H4. This is a fine-tuned version of Mistral 7B optimized for following instructions, good quality for Q&A task. In this cell, we have two functions here. Load quantize model, set up the bits and byte quantize config, 4 parameters to note. Load in 4-bit equals to 2. Load weight at 4-bit precision. BNB 4-bit use double quant equals to 2. Double quantize applies quantize to the quantize constant to save a little extra memory. Bits and bytes BNB 4-bit quant type equals to NF4 normal float 4 format. This is better than plain INT4 because it preserves the normal distribution of transformer weight. BNB 4-bit compute dtype equals to torch.pfloat16 enough even though weights are stored. A 4-bit computation happen in bit 16 for better numerical stability. Initialize tokenizer loads the tokenizer for this specific model. Every model has its own vocabulary and the tokenizer rules. You must use the matching tokenizer, not the generic one. Now let's load the model. This will take 3 to 5 minutes or could be more. It is downloading Zephyr 7 billion from Hugging Face and loading it into GPU memory at the 4-bit precision. You will see a progress bar. Let it complete. Once done, check the GPU memory output. You should see approximately 4 to 5 GB used. So finally download has been finished. It's showing 4 minutes 44 seconds. Just to let you know that it took a lot of time in the different browser. In my different browser, so I have started and that browser exhausted in that option, so I have that uses also I reached to limit, so I have switched the browser and I have run the whole notebook again until here, but this time in this browser window it took only 4 minutes 44 seconds to complete that part. And you can see the GPU memory use 4.57 GB as we have discussed. Now come to our next cell. So we wrap the model in Hugging Face text generation pipeline, then wrap that in LangChain Hugging Face pipeline. This is how LangChain communicates with local model. Device equals to map equal to auto tells it automatically place layer across available device. Max length equal to 2048. Maximum token in one generation. Do sample equals to true with top k equals to 5. Slight randomness in generation, so answer do not feel mechanical. When you see LLM pipeline ready, we are good to build the chain. So let me do that. Yeah, this is the moment we have been building toward. Same LLM, same document, same question, but two different chains. Normal chain uses only the dense retriever, 3 documents, vector similarity only. Hybrid chains uses the ensemble retriever up to 6 document dense plus BM25. So let me copy paste this code. So as we have talked, there are one for normal chain and one for hybrid chain. Let me execute this one. Now, Retriever QA is from LangChain Classic Chain. Note that package name again. Chain type equals to stuff means stuff all retrieved document into the prompt as context. Simple and effective for small numbers of documents. 2 chains created, one naive, one hybrid. Only difference is the retriever passed in same LLM, same prompt, template, same model, prompt template, same model, everything else being equal. Only the retrieval change, that is what makes the comparison clean. Here we have a first query. What is the RAG token model? This is a specific technical term from the paper. The word token is in the context of RAG token is not the same as the word token used everywhere in NLP. Dense search may pull in related documents. but might miss the exact mechanism. Let's see what the naive returns. Read the output. It will likely somewhat vague or mix journal rack concept with the specific rack token mechanism. So here is the output. Now the same question with hybrid retrieval BM25 with specifically find chunks where rack token appears as exact word. Those chunks contain the precise definition from the paper. Look at the answer. Let me execute first. So look at the answer. Let's wait for the answer first. It should be noticeably more precise. The rack token model predict each output token from separately retrieved document. This is actual definition. Dense alone would no guarantee finding the specific passage. So you can easily find the difference between the answers. Query 2. Second query, what is the abstractive question answering? The word abstractive is very specific technical term from the NLP literature. Dense search may find document about question answering in journal, but abstractive specifically refer to the generating answers from by paraphrasing, not extracting exact span. Watch the naive answer. It may be journal or vague. So answer, you can see, use the following pieces of context to answer the question at the end. If you don't know the answer, just say that you don't know. Don't try to make up the answer. Abstractive question answering RAG model can beyond simple extractive QA and answer questions with free from abstractive even when the correct answer. So you can read the answer. Let me go and do that for this hybrid chain. Second query. Now with the hybrid BM25, find chunks containing abstractive as an exact keyword match. The answer should include concrete details, benchmark like MS macro, NLG blue score, the distinction from extractive QA. These are in the paper but required BM25 to locate precisely. More context in better answer out. That is the whole point of hybrid retrieval. This is one of the favorite cell because it shows you exactly what is going on in your LLM. Notice I am using .invoke on retrieve directly, not .get relevant documents. That method is deprecated now in newer LangChain. Always use invoke. Look at the output side by side. Dense retriever 3 documents, ensemble retrieve up to 6 documents. Now you can, let me answer it. You can read the actual content of each chunk. The extra document from BM25 are the ones containing the exact abstractive. They may not be closest to in vector, but they are exactly in topic. That's exact extra context in the is what makes difference in generation quality. Final note here says it all. Richer context for the LLM, more relevant context in better answer out every time. Here are the key takeaways. Okay, so let me give you the 5 things to remember. 1. Naive retrieval misses exact keyword matches. Dense search is powerful, but it has the blind spot. 2. TF-IDF and BM25 are old algorithms, but they are still production standard. Elasticsearch uses BM25 by default. Do not underestimate them. 3. The ensemble retriever alpha weight is your tuning dial. Set is for your domain. Technical docs want more keyword weight. Conversational apps want more semantic weight. 4. More relevant context equal better answer. This is not magic. It is just giving the LLM better material to work. 5. The implementation of 4 LangChain lines BM25 Retriever, Chroma is Retriever, Ensemble, Retrieval QA, that is it. And that's it for advanced RAG hybrid search. We built keyword search from scratch with TF-IDF. We built the full hybrid pipeline with BM25 and dense retrieval. We combined them with the EnsembleRetriever, and we proved side by side that hybrid gives better answer than naive. In the next video, we are going to take this further with Vivet, which has naive hybrid search in, and we add cross encoder ranking on top of what of that for even higher precision. The complete notebook is linked in the description. Star the GitHub repo. This is this if this helped. And one small thing I want to mention, all comments in the notebook that explain each code block in the production notes. The architecture explanation, those are in the committed version on the GitHub. So when you go to the repo, every cell will have full documentation. Today we focused on the code itself and the concept. GitHub has the complete annotated version. Please hit the like, share and subscribe the channel if this, and share this with anyone learning RAG. It generally helps me keep making this content. So thank you so much for watching. I am Mayank Chung. See you in the next one. Thank you.